Underfitting, on the other hand, is addressed by increasing model capacity, improving feature engineering, or training longer. If a model is too simple, we can add layers, add features, or use a more expressive architecture. If optimization has not converged, we may need more training iterations or better learning rate schedules. It is critical to understand that overfitting and underfitting are not binary states but positions on a continuum. There exists an optimal complexity where validation error is minimized. If we plot model complexity on the x-axis and generalization error on the y-axis, we often observe a U-shaped curve. On the left side, models are too simple and underfit. On the right side, models are too complex and overfit. The bottom of the curve represents the best trade-off between bias and variance. In modern deep learning, this U-shaped curve can exhibit more complex behavior, including double descent phenomena. As model capacity increases beyond the point of interpolation, test error may initially increase but then decrease again. This challenges classical intuitions and suggests that the relationship between capacity and generalization is more nuanced than previously believed. Another important dimension is dataset size. A model that overfits on a small dataset may generalize well on a larger dataset. Increasing data generally reduces variance without increasing bias. This is why large-scale datasets are so valuable. They allow high-capacity models to learn robust patterns rather than memorizing noise. We should also discuss the role of noise. Overfitting is fundamentally about fitting noise. Noise can come from measurement error, label errors, or inherent randomness in the data generating process. If labels are incorrect or inconsistent, a sufficiently powerful model can learn those inconsistencies. For example, if 5% of training labels are randomly flipped, a large neural network may learn to predict those flipped labels correctly for training examples, harming generalization. Cross-validation is another tool to assess and mitigate overfitting. Instead of a single train validation split, we partition the data into multiple folds. We train multiple models, each time leaving out a different fold for validation. This provides a more reliable estimate of generalization performance, especially when data is limited. It is also useful to distinguish between interpolation and extrapolation. Overfitting concerns interpolation within the training distribution. Extrapolation refers to performance outside the distribution. A model may generalize well within the distribution but fail catastrophically when encountering out-of-distribution inputs. This is related but distinct from overfitting. A model can be perfectly regularized and still fail to extrapolate because it has never seen similar data. In practical systems, diagnosing overfitting and underfitting involves careful monitoring of metrics. If training loss decreases steadily while validation loss plateaus and then increases, we suspect overfitting. If both losses plateau at high values, we suspect underfitting. However, metrics alone are insufficient. We must consider dataset representativeness, feature leakage, and evaluation methodology. Feature leakage deserves special attention. Sometimes, what appears to be excellent generalization is actually a subtle form of overfitting due to leakage. For example, if future information inadvertently leaks into training features, the model may appear to perform well on validation data that is not truly independent. When deployed, performance collapses. This is not classical overfitting due to model complexity but due to flawed experimental design. Let us step back and consider the philosophical perspective. Overfitting is about mistaking coincidence for causation. The model identifies correlations that exist only in the training sample. Underfitting is about failing to detect meaningful structure. In scientific modeling, both are dangerous. A theory that is too simple misses reality. A theory that is too complex explains everything but predicts nothing. From an information theoretic perspective, learning can be viewed as compressing data. A model that generalizes well captures the underlying regularities that allow compression. Overfitting corresponds to memorizing the dataset without compression. Underfitting corresponds to compressing too aggressively and discarding important structure. In contemporary large language models, overfitting can manifest as memorization of specific training documents. Researchers analyze this by probing whether the model can reproduce rare sequences verbatim. Techniques such as differential privacy and dataset filtering are used to reduce such memorization. At the same time, we want the model to learn general linguistic and semantic patterns. Balancing memorization and abstraction is subtle. In reinforcement learning, overfitting can occur when an agent learns a policy that exploits quirks of the simulated environment but fails in the real world. For example, an agent trained in simulation may learn to rely on rendering artifacts rather than physical principles. When transferred to a real robot, performance degrades. Domain randomization and robust training are used to mitigate this. Ultimately, managing overfitting and underfitting is about managing uncertainty. We do not know the true data generating function. We approximate it from finite samples. The art and science of machine learning lie in choosing model classes, optimization strategies, and regularization techniques that yield robust generalization. As experienced engineers and researchers, you should think in terms of capacity control, data quality, and evaluation rigor. Always ask, is my model too simple to capture the signal? Is it too flexible relative to the data? Are my validation procedures sound? Am I inadvertently fitting noise? In summary, underfitting occurs when the model lacks sufficient capacity or training to capture the underlying structure, leading to high training and validation error. Overfitting occurs when the model captures noise and idiosyncrasies of the training data, leading to low training error but high validation error. The balance between them is governed by the bias-variance trade-off, dataset size, regularization, and model architecture. If you internalize one core principle, let it be this: the objective is not to minimize training error, but to minimize expected error on unseen data. Every design decision in AI architecture and training should be evaluated through that lens.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.